Okay, let's get started for real this time. Um, so broadly speaking, the work I'm presenting today focuses on learning to make sequences of decisions. Perhaps the most obvious application of these sort of techniques are in kind of robotics applications like self-driving cars, but I think they also apply more broadly to things like recommender systems and the kind of growing set of large language chat models because of repeated interaction with the same user. Today, I'm mostly going to be talking about a paradigm for learning to make sequential decisions from data called imitation learning. So with apologies using the word crash here, I'm going to try and talk a little bit how we could try and use it to learn to drive a self-driving car. So let's say we get some set of expert drivers, we stick them in cars that have been instrumented with sensors like LiDARs and cameras, and we have them drive laps around Pittsburgh. Then from this data, we want to learn a policy that allows the car or the truck to do the same. So let's say we think about this very kind of simple problem here, where we have some sort of track we want to do laps around, get data from an expert driving laps around. Let's say their state is something like their X and Y position, and their actions are something like, how much they're turning the steering wheel, how much they're pressing the gas or brake pedal. So the simplest way we could think about solving this problem is just by supervised learning. So we take expert states, expert actions, and we just regress directly between them. We could use something like a mean squared error criterion. And this sort of approach is called behavior cloning. So unfortunately, when we deploy a policy learned via behavior cloning in the real world, we'll often see small mistakes early on lead to larger and larger errors as time goes on, a phenomenon known as compounding errors. What's happening is that the learner only saw states from the expert state distribution at train time, and therefore might not generalize well to their own induced state distribution. So when they end up in a state they haven't seen before, they might make a random choice, ending up in another state they haven't seen before, and continuing to make errors for the rest of the horizon. What's happening here is really just covariate shift, in the sense that the input distribution, the state distribution is changing. So in full generality, the problem distribution shift is impossible to solve, right? If you get tested on input you've never seen before, you have no idea what to predict. But this is where interaction with the environment becomes key. Specifically, interaction allows us to generate samples from the test distribution. So we can actually, drive our car around, take action, see where we end up, and therefore we know the sort of states we would see. The question becomes how we can use this data to actually learn to make decisions well. I'm going to talk about a few different ways of doing this. So one particular approach might be to roll out the learner's policy and minimize some notion of divergence to a collected set of expert demonstrations. So the way I like to think about this is basically like a GAN. So our generator here is a policy, perhaps coupled with a world model to actually give us trajectories. And our discriminator here tries to differentiate between learner and expert trajectories. Then the policy update here is doing reinforcement learning with discriminator as your reward function. These sorts of techniques are called inverse reinforcement learning. Maybe the critical point to take away here is because you're actually doing rollouts in the environment, you can end up in states you haven't seen before at test time. So if you're able to further query the expert, a natural approach is to ask them what they would have done had they been in your situation. And these sorts of interactive approaches are able to prevent compounding errors because they get labels on the test distribution. So more explicitly, we get some states, we ask the expert to label them with the actions they would have taken, train a policy. We roll out that policy, ask for action corrections again, and then kind of aggregate the data, train on all of it. The aggregation here is important basically to stabilize your policy over iterations. If you're familiar with online learning, we're basically running follow the regularized leader to pick policies. And this sort of approach is called Dagger. So putting it all together, we have a taxonomy of imitation learning algorithms. We have offline approaches like behavior cloning. And then if you've accessed the environment, you can try approaches like inverse reinforcement learning that actually compare trajectory distributions. And then we also have approaches like Dagger, which require a queryable expert and try to minimize the difference between learner and expert actions on states from learner rollouts. So this sort of is kind of maybe a kind of a map of the different types of algorithms I'm going to be trying talking about today. So now I want to talk a little bit about what the sort of contributions of the work I've been doing over the last few years are and what I hope to do next. So this is a very long title. I'm going to try and break it down into a few different parts. The first part of the firework I'm talking about is how we can do imitation learning in sort of idealized environments. So this is where there's full observability, and we kind of just see everything we need to make decisions well. So I'm going to first talk about sort of compounding errors in imitation learning and how different classes of algorithms are robust to them or not. I'm then going to talk about how we can have computationally efficient algorithms that are robust to compounding errors. Computationally here meaning minimizing the number of learner-environment interactions. And then I'm going to talk about statistically efficient algorithms, so we can minimize the amount of expert demonstrations required. Then I'm going to talk a little bit about trying to do imitation learning when there's sort of unobserved confounders in your data generating process. I'll get into a little bit more about why this is important in a bit, but I'm going to be talking about two different kinds of unobserved confounders. One is going to be sort of privileged information the expert has access to, but the learner does not. And next is going to be sort of temporally correlated noise in the demonstrations. Then for my post work is mostly going to focus on things that are related to unobserved confounders. So I'm first going to try and talk about how we can apply a very similar set of techniques to the reinforcement learning setting. And then I'm going to talk a little bit about what I'm calling dynamic confounders, or confounders that are directly affected by the learner's actions. Then if we happen to have any time left at the ending, I'll talk a little bit about a project I've been trying to do on trying to learn constraints from demonstrations. Cool. The first part of my prior work is going to be trying to talk about how we can do this sort of interactive learning as efficiently as possible. So I'm going to first talk about compounding errors. And here it's really about how we can make sure our cars don't, go off the rails. Next, I'm going to talk about computational efficiency. We're just going to focus on how we can minimize the number of learner environment interactions. And then third, I'm going to talk about statistical efficiency, which is how we can squeeze the most out of a finite set of expert demonstrations. Let's start off with compounding errors. So I'm going to introduce this idea of mode matching and imitation learning. I'm not going to go through this in too much mathematical detail, but this is sort of the kind of underlying set of proof techniques that I'm going to use for all the works that come after this. So in imitation learning, we're attempting to learn a policy, pi, that matches the performance of the expert, pi e, under some objective function, j. The key challenge of imitation learning is this function is unknown. However, we often know something about this function, right? So for self-driving, we might know it depends on things like avoiding other cars and speed limits rather than the phase of the moon. This means we can often roughly specify the class this function lies in. However, given we don't know which function in this class as the one we actually care about, we can instead attempt to do well under all functions in this class, or equivalently under the worst case function in this class, which very naturally leads to the form of a two-player zero-sum game. And it turns out that basically by doing different decompositions of this performance function j, we can recover the different families of imitation learning approaches. I don't have time to do derivation, but that's sort of the high level point. So the sort of interesting takeaway perhaps is that we can write a very wide set of fireworks in the form of one of these games, either an offline game, an online game, or an interactive game. That means then by analyzing the properties of these games, we can make statements about all algorithms in each of these classes rather than in a particular class. So the first contribution is really deriving matching upper and lower bounds for all algorithms in each of these classes, and to sort of delineate how they handle compounding errors. So maybe one takeaway is that without access to the environment, it's impossible to prevent compounding errors in general. If you have access to the environment with an inverse reinforcement learning approach, you're able to prevent compounding errors. What you do need to compute to do a reinforcement learning interview, which can be rather computationally expensive. If you have access to a queryable expert, interactive approaches can have a performance sort of scales with the kind of particulars of the problem. For certain problems, they'll perform when this number h is close to 1, they'll perform similar to online approaches. And when this number h is close to t, which is the horizon of the problem, they will perform as well. I'll note here that basically epsilon here is a measure of training error, and there's kind of matching upper and lower bounds here. So that kind of, I think, kind of delineates a story as far as compounding errors for each of these families of approaches. Now I want to talk a little bit about computational efficiency. So if you remember what I just talked about on the last slide, it seems like inverse reinforcement learning is sort of the right family of algorithms to use, right? It gets the tightest bounds. The issue with inverse reinforcement learning is that it is rather computationally inefficient because it requires repeatedly solving a reinforcement learning problem. And if you think about this for a second, it's a bit backwards, right? We've reduced the easier problem of imitation learning to repeatedly solving the harder problem of reinforcement learning. Sort of done the reduction in the direction you don't want to do. So let me try and walk through an example of why inverse reinforcement learning is expensive and how we can fix it. So let's say the learner is operating in some sort of MDP that looks like a binary tree. They start at the top, and at each step they choose to go left or right. Let's say we constrain the adversary to pick reward functions. There's 0 everywhere in the tree except at one of the leaf nodes. So maybe at some iteration, the adversary picks this reward function. Then to get any reward on this problem whatsoever, the learner needs to explore this entire tree, namely every single leaf node, of which there are 2 to the h, where h is the horizon of the problem. So this means that even on the first iteration of this procedure, we already have exponential complexity. And then we're going to do this repeatedly at every iteration. So we're going to definitely be rather inefficient. And the question is, how can we speed this up? And our key insight was that when we solve the problem this way, we are ignoring a key piece of information we have, which is that we know the expert state distribution. And we're going to use this in a sort of dynamic programming fashion. So over here, let's say the expert here is here in green, so they always take the action that goes left. So instead of solving one kind of complicated reinforcement learning problem, we're going to solve for a sequence of policies backwards in time in a dynamic programming fashion. So rather doing dynamic programming in terms of like Q values, here we're doing it in terms of policies. So at the first iteration, the learner just picks whether to go left or right on stage in the second to last time step from the expert imitation distribution. And we solve a game where the adversary gets to look at suffixes of left one, to just basically act one action. Now here, we're going to learn to go left. Then we sort of lock this policy in and we back up a step. Now this policy is fixed. We're going to go left at the next time step. And we try to just learn a policy that picks a single left or right action. And we have an adversary that discriminates between vector suffixes of left and two. So we once again go left, and then we lock this policy in, we do this one more time, and then we sort of output these 3 policies. And perhaps the important takeaway here is we don't need to explore every single node in this tree. We're only looking at states from the expert visitation distribution. This means our overall complexity is polynomial in the task horizon rather than exponential. So the main contribution of this work was basically the first general polynomial interaction complexity algorithms for inverse reinforcement learning. So the algorithm I just described, we call MMDP, or moment matching by dynamic programming. There's also a version of this that doesn't learn a sequence of policies and learns a single stationary policy, basically by resetting the learner to a random time step in the expert demonstrations. The intuition is a little bit less clear though, so I wanted to present MMDP. And turns out they work, at least on some Gokul problems. So here you'll see that the 2 algorithms I just described here in orange and teal are much more quickly able to match expert performance than an inverse reinforcement learning algorithm here in gray. And then if we pick a problem that's a hard exploration problem, inverse reinforcement learning has to solve the maze at every iteration, barely gets off the ground, our algorithms are able to do surprisingly well. So yeah, I think the contribution of this part is really polynomial time algorithms for inverse reinforcement learning. And next I want to talk a little bit about statistical efficiency. So what I mean by statistical efficiency is trying to make the most out of a very small set of expert demonstrations. And we're going to derive the min-max optimal algorithm for this problem. So when you have very few demonstrations, estimating the moments that you want to match is hard. So let's try and walk through how we could try and reduce some of the difficulty here. So let's think about just for a single trajectory, what the sort of generative process looks like. So the expert picks some action, state 0, the MDP transitions to the next state, they pick another action, and so on and so forth. And if you think about it, if we're in the sort of inverse reinforcement learning or the online setting, we actually have access to we have the ability to sample from the transition distribution, right? We actually can execute action and see where we end up. So this means that our uncertainty lies purely in the expert actions rather than the transition functions when we think about the uncertainty over the trajectory distribution. Furthermore, we might be able to localize our uncertainty to certain actions or the expert's actions at certain states. So maybe the learner always starts from some start state, but we're very sure what the expert's action is at the start state. But further on, we're less sure. And this means that basically all of our uncertainty lies in the expert actions at some particular states. And this kind of gives an intuition for how you might think about trying to basically better estimate moments. I'm going to give you like a potential algorithm for doing this now. We call this algorithm replay estimation. So the first step is you train a behavior cloning learner. Second is you do rollouts in the environment with this learner. Third is you add these rollouts to your expert dataset, associating a weight with how confident you are about these actions. And then you perform a weighted on-policy mode matching procedure. So this might seem like a very sort of like random algorithm I just pulled out of nowhere, but it turns out it actually has surprisingly strong theoretical properties. More formally, it is actually the minimax optimal algorithm in like the tabular and linear settings. So for those who aren't familiar, basically what this means is that if I take the min over algorithms and the max over MDPs, this will give you the tightest performance bound. A bit more formally, if we think about something like a tabular problem, we sort of get a bound on the maximum difference between learner and expert performance that is tighter here in orange. Then you get either for behavior cloning, which is here in gray, the inverse reinforcement learning, which is here in blue. And we implemented this on some Majoko tasks that have so I guess maybe to sort of sum that up, basically we were able to derive the minimax optimal algorithm for this problem, which gets the best use of a finite set of demonstrations. So I think in short, the contribution of the first part of my prior work is basically computationally and statistically efficient algorithms for imitation learning that are robust to compounding errors. Cool. And now I'm going to talk a little bit about unobserved confounders. I was very proud of that transition. So for those who aren't familiar, what is an unobserved confounder? So let's say we're trying to predict from some variable x to some variable y, both of which are influenced by some unobserved variable u. If we just regress from x to y, because of the influence of u, we won't correctly recover the effect of x on y. In the imitation learning setting, what we're trying to do is find a mapping from states to actions based on expert demonstrations. There is going to be a confounder that affects both states and actions. So I think the natural question at this point is like, well, why should I care about this, right? Why should I care about unobserved confounders? And I think at least my logic is something like this. So I just spent around 20 minutes going through a bunch of fancy bounds for imitation learning algorithms. And if you look at all of these bounds, all of them say that if I can bring my infinite sample trading error, epsilon, to 0, I should be able to perfectly match the expert's performance under an arbitrary reward function. However, that's not what actually happens in the real world, right? It's not as if self-driving cars work perfectly. It's not as if large language models work perfectly. This means, I think, that we sort of oversimplified the problem when we did this idealized analysis. And I'm going to go through a couple examples where unobserved confounders lead to kind of clear failures in imitation learning algorithms and how we can approach those. So I'm going to talk about two different kinds. One is going to be sort of unobserved context or sort of privileged information the expert has access to, but not the learner. The second is going to be temporally correlated noise in the actions of the expert demonstrations. So let's start off with unobserved context. So this is a quote from, I want to say, Young and King's group on a self-driving project. And you notice this sort of like interesting thing where he had a policy that just took the current frame as input and predicted an action, worked okay. He was like, okay, it needs more information, but I'm going to give the last few frames as input. And as soon as he trained the policy with the last few frames as input via behavior cloning, he noticed this really odd behavior happen, which is that the car would start repeating its own past actions. As soon as the car started to turn, it just started driving in circles. So clearly this is not what we want. And I think, you know, if I put on my sort of engineering hat here, I would say, well, I'm not going to add the last few frames as input then. Problem solved, right? But I'm going to try and argue why we actually need the last few frames as input.
Which is the solution in that case.
So I'm going to try and argue why for certain problems we actually do want the last few frames as input, and then how we can prevent this sort of action looping from happening.
Nobody ever said Jan was bad at engineering.
No one did.
So broadly, the problem we're trying to solve here is imitating an expert with some sort of privileged information. I'm going to try and argue that it requires history. So let's say there's some state, you know, the expert responds to it, giving us an action, and the MDP transitions to the next state, you know, keeps going on. And let's say there's some sort of special element of the state, let's call it C here, that the expert observes and uses to guide their actions, but the learner doesn't. So C here is a an unobserved confounder in like the proper causal inference sense. So if C just affects their actions and it's not reflected in the states whatsoever, we might be hosed as far as accurately imitating the expert, right? Like if our sensors don't pick up on a stop sign, how is our car supposed to know to stop? So okay, let's make this problem a little bit easier. And let's say there's also edges from C to the observed state. So for a stop sign example, maybe you see every other car around you slowing down. And then if you see this happening for long enough, you might rationally conclude that your car should slow down as well. And this sort of accumulation of evidence over time is only possible when we pass past states as input to our policy, or really past observations. So more formally, what we're trying to do is imitation learning in a POM-DP here. So an MDP, your state is, usual MDP state, but for a POM-DP, your state is instead a belief state, which is a distribution over the sort of unobserved part. In the sort of like policy analog of this, instead of our policy just being a function of the current state, it's instead a sequence model that takes as input the last few states and actions. Okay, so then you might well think we can just do something that looks like behavior cloning with a sequence model, and we're done. Unfortunately, we're going to have that problem that Jan found out. I'm going to try to explain why it happens, and then how interaction can fix it. So I'm going to think the simplest possible problem in which this sort of looping happens. And this is a problem, it's just going to be a simple multi-arm bandit. So we're playing a very simple multi-arm bandit where only one arm per episode gives a learner reward. This one gives the reward, all the rest are 0. And the identity of which arm gives you a reward is going to be the context that's revealed to the expert, but not to the learner. So if we only allow the learner to interact with the set of arms once, they have no ability to do better than random chance, right? They just have to pick an arm at random. But if we instead allow them to repeatedly interact with the same set of arms and give them feedback of some accuracy of whether they pick the right arm, one might hope that given enough time, they can narrow down which arm is the correct one. So this seems like a relatively simple problem. Let's implement it and see what happens. I'm going to kind of contrast two different algorithms here. One is going to be an on-policy algorithm like Dagger, and another is going to be an off-policy algorithm like behavior clone. So here the x-axis is how often the expert makes a mistake. The y-axis here is how often your feedback is flipped. So when your feedback is flipped with 50% probability, no algorithm should learn well. That's why the dots there are red.
Can you remind us what flip means?
Flip means I told you that you got the right arm when you got the wrong arm, or vice versa. The green dots here mean we're able to map actual performance. So we are sort of uniformly consistent outside of a part where it's impossible. In contrast, if you look at behavior cloning, you see these sort of phase transitions, as Drew likes to say, where a very small perturbation of problem parameters leads to a very different result. So your algorithm goes from being consistent to inconsistent. So the question is, what's actually happening in one of these red dots? Let's try and dive into that. So this is one of these dots where the on-policy algorithm works well, but the off-policy one doesn't. What you see is that the off-policy algorithm here predicts the correct arm with probability equal to random chance. There's k arms, and there's k equal to 5 for this problem, so it gets it right with 20% chance. Which is the on-policy algorithm very quickly figures out that, okay, I'm pulling the wrong arm, I should switch to the right arm. So if you actually look at a single trajectory of what the off-policy algorithm does here, at the first time step, it says no information. It has a kind of uniform prior over which arm is the best, so it picks a random one. Then for the rest of the episode, it just keeps pulling that arm over and over again. Completely ignoring the feedback it gets that it's pulled the wrong arm. So maybe let me try and kind of synthesize these observations. So first, the on-policy results tell us that, early on, it's hard for us to do well. We have no information. We don't know which arm is the right one. As you remember, the sort of orange one started off at 0. But then given enough time, we're able to eventually act like the expert did. So this means we're sort of in an asymptotically realizable problem where early on, no learner can act like the expert did because they don't have enough information. But given enough time steps of interaction, you can eventually figure out how to act like the expert did. But then off-policy approaches, even though they have the information to do this, just choose the wrong policy. I'm going to try and give you an intuition for why this happens. And it looks something like this. So when you get this sort of hidden context or privileged information, this means we're in an asymptotically realizable problem, which means that all policies are going to have non-zero early error. This means that we're going to have covariate shift. And as I argued in the first part of this talk, offline algorithms are provably not robust to covariate shift. So this means that offline imitation learning is going to fail with privileged information. I was also very proud of that animation.
I hope that didn't take long to make.
Oh, I spent a full few hours on that. So the informal theorem here is basically that off-policy learners will have a value difference with respect to the expert bounded by the sum of their errors, while on-policy learners will have one dependent on their asymptotic error. Because everyone makes errors early on, right? The first term will be non-zero, but the second one will be zero for problems where you can figure out what's going on. I'll also note this is not just a problem that shows up on this very sort of toy bandit problem. It also shows up on slightly less toy problems. So here I picked one of the sort of the Gokul style environments, and I took like a multitask version of it, and I gave the expert access to the task, but I didn't tell the learner what the task was. And I ran like behavior cloning and dagger on this. You'll see this sort of interesting thing where if I run dagger, then I run dagger with a even smaller psychology class, basically performs the same, maybe slightly better in terms of asymptotic error. But behavior cloning actually gets noticeably worse when you give it extra information. And this sort of, I guess, confirms the sort of theoretical statement I just made, and kind of also, I guess, echoes what Jan found in his work. So maybe the takeaway from this part of the talk is that we've shown both in theory and in practice that interactive imitation learning is robust to privileged information, but offline imitation learning is not. I'm now going to talk about another class of confounders, which are going to be called temporally correlated noise, or TCN for short. So this is based on an example from one of Andrew Ng's papers. I wanted to get one of the autonomous helicopter papers, and you notice there were sort of temporal correlations in some of his data that was sort of preventing the imitation learning algorithm from working correctly. So what he did is he just like tossed out a large amount of the data so that, you know, he didn't have correlations. This does not seem like the right approach. I'm going to try and come up with a slightly better one now. Let me go through an example that sort of mirrors what Ingadal observed in practice that gets sort of at the heart of what makes TCN hard. Let's say we consider the problem of trying to learn to fly a quadcopter by imitating an expert pilot. And let's assume that the joystick the expert's using to control this quadcopter is a bit faulty. So what happens is that it's a bit sticky, and as soon as the expert goes a little bit left, it kind of swerves a bit too much. So naturally, then you're going to have a sort of trajectory in which you're not going perfectly straight. Now, let's say I apply an algorithm like behavior cloning to this data. Well, what's going to happen is that the learner is going to pick up on the correlation that being a little bit on the left is usually followed by going more to the left. And if they ignore the root cause of this correlation was the sort of stickiness of the joystick, they might attempt to reproduce the swerving behavior at the expert. So this is not ideal. We'd like to learn to fly straight. And let me try and formalize what's happening here and then how we can fix it. So let's say there's some state the expert responds to, you know, the MVP transitions to the next state. I'm going to say there's some sort of temporally correlated noise variable, an unobserved confounder U here, that affects pairs of actions. If we try to learn a policy via behavior cloning, that is by regressing from states to actions, we can produce inconsistent estimates of the expert's policy. This is because the temporally correlated noise both affects the next action, as well as traveling through the dynamics to affect the current state. This means we have the same noise variable affecting both our x's and y's, which means regression is no longer consistent. So then the learner can kind of latch onto these various correlations and try to explain it away by misattributing the swerviness to some element of the state. And this is what leads to behavior cloning failing. What I'm talking about today are methods that can learn to fly as straight as the expert did in the demonstrations without requiring sort of an interactive expert. More generally, the methods I'm talking about here are meant to handle temporally correlated noise and sequential prediction. So the key kind of technique we're going to use is something from econometrics called instrumental variable regression. I'm going to go through this at a very high level. So let's say there's some x and y we're trying to predict a relationship between, both of which are affected by some unobserved confounder u. So ideally, what we'd like to do is do a randomized control trial on set X. But if we don't have the ability to perform interventions and just have observational data, we can get a similar effect by conditioning on an independent source of randomness, which we call an instrument, and here is denoted as Z. So the kind of key idea of IVR, in a very vague sense, is that we can predict from X condition on Z to Y condition on Z to recover the causal relationship. You might say, okay, that's fine and dandy, but what is an instrument for this problem? Well, it turns out that we can use the past state as instrument. And this is a really cool idea. I want to say the first place I saw this was in like the least squares temporal difference learning paper, but I think at least Drew and I learned about it from one of Jeff's papers. But graphically, this corresponds to the fact that Z and U sub t here are deseparated. So by using the past state as the instrument, we can derive two different instrumental variable imitation learning algorithms. I don't have time to talk about the details, but one is of a sort of generative modeling flavor, and one is of a game theoretic flavor. We actually implemented these on some Majorca tasks, and they worked great. So here, the data has confounders in it. Our algorithms, which are here in orange and teal, are able to maximize performance, while something like behavior coding isn't able to do so. So in short, the contribution of this part of the talk is algorithms that are robust and poorly correlated noise and the expert demonstrations. So maybe to summarize the sort of unobserved confounders part of this talk is that we have imitation learning algorithms that are robust to multiple classes of unobserved confounders. So putting it all together, we have algorithms that are both kind of statistically and computationally efficient and robust to compounding errors, as well as algorithms that can kind of move beyond this idealized setting and actually handle situations with unobserved confounders. So this is sort of the kind of roadmap to start off with. So we've gone through the sort of two parts of prior work, and I'm going to talk a little bit about post work. So each part of this proposed work is trying to address something that I think is somewhat limited about my prior work. The first part is going to be about how we can try and apply a very similar set of techniques to the reinforcement learning setting. The second is going to be about what I'm going to call dynamic confounders. So one sort of oddity with both of the prior works I presented in the causal setting is nothing the learner can do can actually affect the confounder, right? Like they can't affect the context, nor they can affect the temporally correlated noise. But I think for a lot of problems, you actually can affect the confounder. And the question is how you can learn well for that sort of problem. And then if we have any time at the end, I'll talk a little bit about trying to learn safety constraints from demonstrations. So let's start off with this one over here. So let's say we observe some doctor interacting with patients. So, a patient comes into the clinic and they observe certain things about them. Maybe they observe their temperature, some of their vital signs, something like that. And then they make a decision of whether to give them some sort of treatment or not. Maybe they give them some sort of medicine or just send them home. Let's say we observe a lot of data of this form. And we also observe the patient outcomes. So we know whether they got better or worse. And our goal is, from this data alone, to learn a decision support system. And our decision support system is going to be here some sort of computerized agent that has a different observation space. So quite naturally, humans and people have different observation spaces. And we kind of need to account for this. And specifically, what we want to learn is something that is able to sort of improve upon the baseline policy. We're trying to learn a policy pi that maps on this different observation space, such that if I mix an epsilon fraction method in with the pre-existing policy, we get a better performance than the baseline doctor policy. So with this setup, you might be like, okay, I know how to solve this problem. I'm just going to estimate the Q values and maximize them, right? So more formally, this sort of direct kind of Q value estimation says, I'm going to estimate the Q values from the data here. I'm going to just put a regression model, and then I'm going to just pick the greedy policy to maximize. Seems simple. Of course, though, given it's labeled attempt 1, it's not going to work. And let me kind of walk through, I implemented basically the example I just talked about, and it really doesn't work. So here, alpha is the probability of having a sort of underlying condition, and epsilon here is the kind of probability the doctor makes a mistake. And I kind of want to draw your attention here to this sort of lower left triangle. And this is a really interesting kind of triangle where what's happening is that very few people ever got cancer, and the doctor very rarely makes mistakes. So every time the doctor prescribes someone cancer, they get better. Sorry, try someone chemotherapy, they get better. So this means that the greedy policy is going to suggest giving everyone chemotherapy. If we were then to mix this policy with the kind of doctor's policy, we would be giving a bunch of people chemotherapy who don't actually need it. The core issue here is basically that the Q values are confounded. More formally, it's that the sort of regression we fit here is not equal to the actual causal effect we want to estimate. You can see this perhaps by looking at the kind of graphical model we're looking at in this work. So at train time, or the data that's collected, the green arrows active in the sense that the doctor is making decisions based on this O1 space. But then we are doing regression based on this separate O2 space, which means we're regressing on the wrong set of features, which means we're going to estimate things incorrectly. So how do we go about fixing this? So I'm going to apologize in advance for going through a bunch of math that is either going to make a lot of sense or no sense. But here we go. So there's this thing called the backdoor adjustment, which basically says that if we want to estimate the causal effect of A on Y conditioned on covariance X, we can basically do this sort of density ratio correction. What we do is we first estimate it for each AX, and then we basically re-rate it by this particular density ratio. For our problem, kind of just substituting the symbols in, what we do is we estimate the Q value for every action and pair of observations, and then we basically use the density ratio correction to sort of change it from this space to the space of O2. This is an interesting approach, but perhaps the challenge with it is that it requires actually seeing both O1 and O2. So maybe it's in the data we also get everything the doctor observed, but in practice, it's not as if the doctor's going to be able to write down everything we observed. We might only have access to O2. And the question is how we can still estimate the causal effect. And for that, we're going to use something called the proxy correction, which is, I think, in part due to Chechkin et al. So the proxy correction says we have a graphical model that looks like this. And basically, under some assumptions, if we're able to find a G that satisfies this conditional mode restriction, the causal effect of A on Y, conditional covariance W, is just equal to G. For our problem, the confounder here is the observation we don't see. Our proxies Z and W are the past and current observation, and we're trying to estimate the effect of the action on the discounted sum of future ones. So what this means is if we can find a function G that satisfies this expression, we're then able to just use it to estimate the causal effect. So it is the Q function. And we're able to derive a two-player zero-sum game to allow us to efficiently estimate this, to efficiently find a G that satisfies these initial moment restrictions. But yeah, so maybe the kind of takeaway from this part is that we can also have these sort of unobserved confounders show up in other settings like reinforcement learning, and a slightly different set of techniques can be applicable for that problem. The next problem I'm going to talk about are dynamic confounders. So once again, these are problems where you don't have a sort of static piece of unobserved information that influences the behavior, whatever you're trying to model. It's something that actually evolves over time in response to what your policy does. I think the most kind of canonical example of this in my head is that when you have repeated interaction with the user. So let's say we have some sort of user and they're interacting with the recommender system. You know, the recommender system gives them content and they respond in some way, maybe by like clicking on a video, liking certain posts, stuff like that. And let's say they make these decisions based on some preferences X in their head. Importantly, preferences here are unobserved. But they influence the relationship we care about, what they're going to do. The core issue is that rather than just being a static thing, people's preferences evolve over time. When you show them different content, what they want to see next changes. So in full generality, trying to estimate user responses here will be solving a really, really hard POM-DP. So I'm going to try and make a few assumptions to make this a bit more tractable. So the main assumption I'm going to make is that we have a known user choice model. So I'm going to assume users follow a sort of Boltzmann rational or maximum entropy or exponential family distribution, which says that their response to a certain piece of content basically follows this sort of form here. And I think the kind of key point I want to say here is that I'm assuming we know the set of features here phi, and the only kind of source of uncertainty here are is the fact that we don't actually know their preferences X. A different way of putting the point I just said is that this sort of known user choice model assumption gives us an observation model in the sense that by looking at the distribution of responses people actually had to some piece of content, we can estimate how good a particular preference vector is, and we can try and adjust it over time to be more accurate. So I think the perhaps most obvious thing to do here would be, okay, we have an observation model. I'm just going to solve the POM-DP. So even with an observation model, even with an observation model, though, tiling the preference space is going to be intractable. So let's say you have some space of preferences. To actually run a POM-DP solver over a continuous space, you sort of need to, cast an epsilon net over it. And if we ran something like Jeff's point-based value iteration algorithm, we would basically need to discretize it to find an epsilon optimal policy. We would need to discretize the space to size epsilon. This means you're going to pay exponentially the dimension of the space, which means that if your preferences are some high-dimensional vector, as they often are in practice, this is a completely intractable approach. So I want to now think about how we can do this more efficiently. I'm going to introduce one other piece of structure to help the learner, which are going to be called preference dynamics models. So these are going to be ways our potential options for how people's preferences could evolve over time. So maybe one option here is that no matter what content you show them, A here, people's preferences stay the same. So this is just basically an identity map. We see X again. The next might be that no matter what content you show them, what they like more is just what's popular. So maybe they just look at the charts on Spotify, they just pick whatever is most popular. Maybe another one could be something like their preferences mix over time. So what they do is whatever content you show them, they end up liking more over time, and they want more content like that. And the key question I'm going to try and answer is how we could use such models to help with preference estimation. So you might just say, okay, I'm going to try and run some sort of online learning algorithm using one of these models in some way, maybe using some predictions from it, and maybe I get something to work. But there's a bit of nuance in how you actually do this. So let's say I just kind of look at all the data I have for my set of users, and I run some sort of static regret algorithm. Think of something like just gradient descent. The issue is that a static regret algorithm competes against the best single option in hindsight. This means it would find the best estimate of their preferences over all the data, which is not what we want. We know the preferences are actually evolving over time. So rather than competing against a single fixed preference, we want to dynamically track how preferences evolve over time, which means we can't run a static regret algorithm. We have to run a dynamic regret algorithm. So the particular one I'm going to use in this work is something called dynamic mirror descent, credit to Hall and Willett in 2013. Maybe to break this equation down a bit, basically we are running online gradient descent here, and then we're doing a projection step using the preference dynamics model. The particular form here doesn't really matter, though. Maybe the main takeaway is that we want to use an algorithm that competes against sequences rather than just a particular fixed preference. And then a kind of cool idea that I want to say I learned from Aladazan is that if we run a tracker for each of these preferences in parallel, we can then dynamically choose between them via just a standard static regret algorithm. So we could just run something like multiplicative weights to kind of aggregate these over time. So the idea is basically we can kind of shell out the tracking over time to a learner that just handles that. And then we can select between learners based on the user's behavior online. So this just handles the prediction part. I've also spent a good amount of time thinking about the planning part. I am a little bit less certain about that algorithm though, so I didn't put any slides together on it, but I'm happy to talk about it afterwards. But yeah, that is an approach I'm thinking about for handling dynamic confounders. We are basically at time. So if you want, I can talk about inverse constraint learning, or we can sort of just open it up for questions. I'm okay either way.
Maybe just say what the inverse constraint learning problem is, and we can bring up the question.
Sounds good. So let's say we have some robot operating in a kitchen, and we want it to perform a variety of tasks. Maybe some are making a sandwich, maybe maybe another one is cleaning off the table. But no matter what tasks they're performing in this environment, there are a shared set of safety constraints we want to be true for all tasks. One example might be is that we never want them to break a plate. The question then becomes, okay, if I give you demonstrations of a person performing a variety of these tasks, how could I try and learn this underlying constraint that is true for all tasks? That's sort of the problem set. Okay, so with that, maybe we can open up for questions.
That sounds great.
I'm gonna stop sharing my slide.